We use the word related all the time, right? Two friends, they have a close relationship. Two cities, they're connected by a highway. It's like there's this link.
It's like an inherent connection, yeah.
And that's kind of where math starts too, believe it or not.
Oh, absolutely.
We've got these excerpts from a Class 12 mathematics textbook. And they point out that this whole idea of a relation in math, it comes from that basic human understanding, seeing how two things connect.
It's fascinating how math formalizes that.
So we're gonna do a deep dive today into the world of mathematical relations and functions.
Sounds good.
And we're talking about different ways things can be related, from like no connection at all
Right.
to every possible connection.
Total connection.
We'll look at things like reflexivity, symmetry, transitivity,
Those are key properties.
which basically tell us about the nature of these connections.
Exactly.
Then we'll get to equivalence relations, which are super useful for grouping things together.
They act like sorting mechanisms,
And then we'll move on to functions.
which are kind of like relations with specific rules.
Yeah, very well-behaved relationships, you could say, where each input gives you one output. And we'll explore different types of functions too, like one-on-two bijective.
All fascinating stuff.
The goal today is to show you how these concepts can help you see underlying structures, connections in all sorts of places.
Even where you might not expect them.
Okay, so let's jump right in. The textbook starts off with the formal definition of a relation. And bear with me here, it sounds a bit technical, but it's actually pretty straightforward. A relation R from a set A to a set B is a subset of their Cartesian product, written AA.
Okay.
Now, that Cartesian product, AAB, is simply the set of all possible ordered pairs, where the first element comes from set A and the second from set B.
Right, so you're pairing up elements.
Exactly. So a relation is basically a collection of some or all of these possible pairs. To make this a bit more concrete, the book gives some great examples using students in Class 12 and Class 11.
Oh, that's a good way to illustrate it.
Yeah, so we could have a relation like A is the brother of B.
Okay.
Or A is the sister of B.
Lisa?
A's age is greater than B's age.
Right.
A got fewer marks than B.
Okay.
Or even A lives in the same neighborhood as B.
So these are all connections between a student in Class 12 and a student in Class Parcel.
Precise.
And each of these connections you just described defines a specific set of ordered pairs.
Right. So, for example, the relation A is the brother of B would be the set of all pairs where A is a Class 12 student, B is a Class 11 student, and A happens to be B's brother.
Right. But here's a crucial point. In everyday language, we usually think of a relation as having some obvious, recognizable link. But mathematically, it can be any subset of those ordered pairs. It doesn't have to make intuitive sense in the way we normally think about relationships.
That's a good point. It could be completely random.
It could. But when there is a rule or condition defining our relation, the textbook gives us a way to write it down.
Okay, how's that?
If the ordered pair, AB, belongs to our relation R, we can write ABR,
Okay.
which simply means the pair A and B is part of the relation R.
Got it.
And we can even shorten it further and write ARB, which reads A is related to B under the relation R.
So it's like shorthand. Now, the textbook then goes on to categorize relations into different types.
This is where it gets interesting. We start to see some real structure.
And they begin with the most extreme cases, the empty relation and the universal relation.
Two extremes.
So the empty relation, that's where within a set A, no element is related to any other element.
So nothing is connected.
Exactly. The relation R is just the empty set.
Which is always a subset of AA.
And the book gives a perfect example. In a boys' school, if we consider the relation, A is the sister of B, well, that's an empty relation.
Because there are no sisters.
Simple as that.
It's a relation where the condition can never be met.
Then we have the opposite, the universal relation.
Connection.
Every element in set A is related to every other element, including itself.
So the relation R becomes the entire Cartesian product, AAA.
The book uses the same boys' school example, but with a different relation. The difference between the heights of any two students, A and B, is less than 3 meters.
Now, in a typical boys' school, everyone's height difference is going to be well within that range.
So everyone is related to everyone else under this condition.
Exactly. It's a universal relation.
Okay, so empty relation is total disconnection. Universal relation is total connection. And the book calls these trivial relations.
Yeah, they're kind of the simplest cases.
Now let's move on to the more interesting types: reflexive, symmetric, and transitive.
These properties tell us more about the nature of the relationship between elements.
So let's start with reflexive. What does that mean?
A relation R on a set A is reflexive if every single element A in A is related to itself. So for every A in A, the pair A has to be an element of R. It's like a self-referential relationship. Every element has a connection to its own identity.
Got it. What about symmetric?
A relation R on a set A is symmetric if, whenever an element A1 is related to an element A2, then A2 is also related to A1.
It goes both ways.
Exactly. If A1, A2 is in R, then A2, A1 must also be in R for all A1 and A2 in A. It's like a two-way street.
Okay, symmetry implies a reciprocal relationship. And lastly, transitive. What's that about?
A relation R on a set A is transitive. If whenever A1 is related to A2 and A2 is related to A3, then A1 is also related to A3.
That's like a chain reaction.
In a way, yes. If you have those links A1, A2, and A2, A3 in R, then the link that completes the chain A1, A3 must also be in R.
It's like if A is a friend of B and B is a friend of C, then A must also be a friend of C.
Exactly. Though friendships in real life aren't always transitive. But in math, for a relation to be transitive, it has to hold true for all elements. Now, the textbook uses some great examples to illustrate these properties.
Yeah, examples are always helpful.
So example 3 talks about lines in a plane, and the relation is perpendicular to.
Okay.
This is a brilliant example because it shows us a relation that is symmetric, but neither reflexive nor transitive.
Okay, let's break that down.
So perpendicularity is symmetric. If line L1 is perpendicular to line L2, then L2 is also perpendicular to L1.
Makes sense.
But it's not reflexive because a line can't be perpendicular to itself.
Right.
And crucially, it's not transitive.
How so?
If L1 is perpendicular to L2 and L2 is perpendicular to L3, then L1 and L3 are actually parallel to each other, not perpendicular.
Ah, I see. So we have L1, L2 in the relation, L2, L3 in the relation, but L1, L3 is not in the relation.
Precisely. It shows that a relation can have one of these properties without having the others.
It's not all or nothing. What about the next example?
Example 4 looks at a specific relation R on the set 1, 2, 3, defined as R equals a set containing 1, 1, 2, 3, 3, 1, 2, and 2, 3.
Okay, bit more abstract.
It is, but it demonstrates a relation that is reflexive, but neither symmetric nor transitive.
Okay, how do we know that?
It's reflexive because it contains 1, 1, 2, 2, and 3, 3, meaning every element in the set is related to itself.
Right.
But it's not symmetric because we have 1, 2, and R, but the reverse 2, 1 is not there.
Okay, so the two-way street rule is broken.
Exactly. And it's also not transitive. We have 1, 2, and 2, 3 in R, but the link that would complete the chain 1, 3 is missing.
So again, these examples really show how these properties can exist independently.
I don't have to go hand in hand. Now, this brings us to a special type of relation called an equivalence relation.
Equivalence relation, the name kind of gives it away. It's about things being equivalent in some way.
Exactly. An equivalence relation is a relation on a set A that satisfies all three of those properties we just talked about: reflexive, symmetric, and transitive.
So it's like the trifecta of relations.
You could say that. It's a powerful concept because it lets us group elements together based on a shared characteristic.
The book uses the example of congruent triangles.
A classic example. If T is the set of all triangles in a plane, and the relation R is congruent to, then this is an equivalence relation.
Okay, let's see why.
Well, congruence is reflexive because every triangle is congruent to itself. That's obvious, right?
Sure.
It's symmetric because if triangle T1 is congruent to triangle T2, then T2 is also congruent to T1.
Right.
And it's transitive. If T1 is congruent to T2 and T2 is congruent to T3, then T1 must be congruent to T3.
So it ticks all the boxes.
Yeah.
Reflexive, symmetric, and transitive.
Precisely. That's why is congruent to is an equivalence relation. Now, example 5 in the book gets a bit more abstract. It defines a relation R on the set Z of all integers, where an integer A is related to an integer B if and only if 2 divides the difference AB.
Okay, so two integers are related if their difference is an even number.
That's the condition. Now, let's see why this is also an equivalence relation. First, it's reflexive. For any integer A, the difference AA is 0, and 2 divides 0.
Okay, that makes sense.
Next, symmetry. If 2 divides AB, then AB is even, which means BA, which is just the negative of AB, is also even.
Right, because the negative of an even number is still even.
Exactly. So 2 divides BA as well. So if AB is in the relation, then BA is also in the relation. It's symmetric.
Okay, what about transitivity?
This one takes a little bit of algebra. If AB is an R and BC is an R, it means 2 divides AB and 2 divides BC. So we can write AB as 2 times some integer k and BC as 2 times some integer m.
Okay, I'm following.
Now, if we look at the difference AC, we can rewrite it as AB plus BC. Substituting our expressions with 2k and 2 meters, we get 2k plus 2 meters, which is the same as 2 times k plus m. Since k plus m is also an integer, AC is divisible by 2.
So AC is also in the relation.
Exactly. This proves that the relation 2 divides AB is transitive and therefore an equivalence relation.
Okay, so we've established that it's an equivalence relation. Now, this is where the book introduces the idea of equivalence classes.
And this is a very important concept.
What exactly are they?
Think of it this way. An equivalence relation partitions a set into disjoint subsets, kind of like sorting elements into different boxes based on a shared characteristic.
Okay.
In our example with integers, where 2 divides the difference, let's see what happens. All even integers are related to each other because the difference between any 2 even numbers is always even, and they're all related to 0.
Makes sense.
Similarly, all odd integers are related to each other, and they're all related to 1.
Because the difference between two odd numbers is also even.
Precisely. So the set of all even integers forms one group, and the set of all odd integers forms another group. And no even integer can be related to an odd integer under this rule.
Right, they're in separate boxes.
Exactly. And these boxes are what we call equivalence classes. The set of all even integers is the equivalence class containing 0, denoted by 0.
Okay.
And the set of all odd integers is the equivalence class containing 1, denoted by 1.
So 0 represents all even numbers, and 1 represents all odd numbers.
That's a great way to put it. Now here's the key takeaway. An equivalence relation partitions the original set into these mutually exclusive equivalence classes, meaning they don't overlap, and their union gives us back the entire original set.
So it's a complete and clean division based on the relation.
Precisely. It's like creating order out of a set by grouping elements that share a specific property.
So within each equivalence class, everything is related to everything else, and nothing in one class is related to anything in a different class.
That's exactly right. And the book also points out that this process works in reverse.
What do you mean?
If you have a partition of a set into non-empty disjoint subsets, you can actually define an equivalence relation based on that partition.
How so?
2 elements would be considered related if and only if they belong to the same subset in the partition.
Oh, I see. So the partitioning itself can give rise to an equivalence relation.
Precisely. The book uses an example with multiples of 3.
Okay, tell me more.
You can partition the set of integers into 3 subsets. Those perfectly divisible by 3, those that leave a remainder of 1 when divided by 3, and those that leave a remainder of 2.
Okay, so 3 separate groups.
And if you look at the relation 3 divides a b, it turns out that these 3 subsets are exactly its equivalence classes.
Ah, that's interesting. So the equivalence class of 0 under this relation would be all multiples of 3.
Yes. The equivalence class of 1 would be all integers that leave a remainder of 1 when divided by 3.
And the equivalence class of 2, all integers leaving a remainder of 2.
Exactly. So there's this beautiful back and forth between equivalence relations and partitions.
It's like 2 sides of the same
A
coin.
very insightful way to put it.
Now, the textbook then smoothly transitions to the topic of functions, mentioning that they're actually special kinds of relations.
Which is a natural progression.
Okay, so how are functions related to relations?
A function from a set X to a set Y is a special type of relation where every element in X is related to exactly one element in Y.
So it's a very specific kind of relation.
Yes, it's very well defined. Think of it as a rule that assigns each input a unique output.
Okay, that makes sense.
Now, within functions, we have different classifications. 1, 1, which is also called injective, onto, also known as surjective, and functions that are both, which are called bijective.
Okay, let's unpack those. Starting with or injective functions. What defines them?
A function f from x to y is 1, 1 if distinct elements in x always map to distinct elements in y.
So no 2 different inputs can have the same output.
Exactly. Each input has its own unique output. The book refers to figure 1.2i and 4 as visual examples.
Okay, I'll have to check those out later. What about onto functions or surjective functions? What's their defining characteristic?
A function f from x to y is onto if every element in y is the image of at least one element in x.
So you can reach every element in the target set y by applying the function to some element in the starting set.
X, precisely. It's like the function covers the entire target set.
Got it. And then we have functions that are both 1, 1 and onto, which are called bijective.
Bijective functions are special because they create a perfect pairing between the elements of x and y. Each input has a unique output, and every output has a unique input that maps to it.
So it's a one-to-one correspondence.
Exactly, and the book shows this in Figure 1.2.
Okay, so the book then uses a bunch of examples to really nail down these definitions.
Examples are great for making things concrete.
So example 7 talks about a function where set A is a group of 50 class X students, and the function maps each student to their unique roll number.
This is a great example of a function that's 1, 1 but not onto.
Let's break that down.
Since each student has a unique roll number, no two students can have the same roll number. So the function is 1, 1. However, if the roll numbers are from 1 to 50, then a number like 51 is not the roll number of any student, meaning it's not an output of the function. So there are elements in the target set that aren't covered by the function, which means it's not onto.
Okay, I follow that. What about example 8?
Example 8 defines a function as fx equals 2x, where both the input set and the output set are the natural numbers.
Okay.
And this function is also 1, 1, but not onto.
Okay, let's see why.
If we have f back 1 equals fx2, that means 2 by 1 is 2 by 2, which implies by 1 equals by 2. So it's definitely 1, 1. However, if we take the number 1 in the output set, there's no natural number x that we can plug into the function to get 1 as the output.
Right, because 2 times any natural number will always be even.
Exactly. So the function is not onto.
What about example 9?
Example 9 uses the same function fx equals 2, but this time both the input set and the output set are the real numbers.
Okay, so we've expanded the sets.
And by doing that, the function actually becomes both 1, 1 and onto. It's still 1, 1 as we saw before, but now for any real number y in the output set, we can find a real number x such that fx equals y. We just take x to be y2.
Right, so if y is 4, then x would be 2 and f2 would 4.
Exactly. So every real number in the output set has a corresponding input, making it onto.
Okay, that's interesting how changing the sets can change the properties of the function.
It highlights the importance of the sets we're working with. Now, example 10 introduces a piecewise function.
Piecewise function.
Yeah, it's a function that's defined differently for different parts of the input set.
Okay, what's the specific function?
In this case, the function is defined from the natural numbers to the natural numbers. It's defined as f1 f2 equals 1. And for any x greater than 2, fx by 1.
Okay, a bit more complicated.
It is, but it shows us a function that's onto but not 1, 1.
Right, let's see why.
It's not 1, 1 because both 1 and 2 in the input set map to the same output, 1.
Right, so 2 different inputs have the same output.
However, it is onto. For any natural number y in the output set, we can find an input that maps to it. If y is 1, well, we have both 1 and 2 in the input set that map to it. If y is any other natural number, say 3, then y plus 1, which is 4 in this case, will map to y.
Because f4, y is 4, 1 equals 3.
Exactly. So every natural number in the output set is covered, making the function onto.
Okay, I get it. What's the next example?
Example 11 looks at the function fx equals by 2, where the input and output sets are both the real numbers.
Okay, familiar territory.
This one is a classic example of a function that's neither 1, 1 nor onto.
How come?
It's not 1, 1 because, for example, f1 and f1 both give us 1. Two different inputs map to the same output.
Okay.
And it's not onto because there's no real number, x, that when squared gives us a negative number.
Right, the square of a real number is always non-negative.
So there are elements in the output set, the negative real numbers, that have no corresponding input.
Makes sense.
Now, example 12 gives us another piecewise function. This one is defined as fx, x plus 1 if x is odd, and fx equals by 1 if x is even.
Okay, another interesting one.
And this function is both 1, 1 and onto, which might be a bit surprising at first glance.
So how do we know that?
To check if it's 1, 1, we need to make sure that if f by 1 equals f's 2, then by 1 must equal by 2.
Right.
Now, we have to consider different cases. If both by 1 and by 2 are odd, then is 1 plus 1 plus 1 and by 2 plus 1, which implies by 1 equals by 2.
Okay.
If both are even, then I1, 1 equals by 2, 1, which also implies by 1 by equals by 2.
Right.
And if one is odd and the other is even, their function values can't be equal because one will be even and the other will be odd.
Ah, clever. So it's definitely 1, 1. What about onto?
To check for onto, we need to see if every natural number in the output set has a corresponding input. If y is even, then y plus 1 is odd, and fy plus 1 plus 1 plus 1 plus 2, wait, no, fy plus 1 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 plus 2. If y is even, we need fxy. If x is odd, x plus 1 equals y1y, so xy plus 1, which is even if y is odd. So in all cases, we can find an input that maps to the desired output, making the function onto.
Okay, that one was a bit tricky to follow, but I see the logic.
It requires careful consideration of all the possibilities. Now, examples 13 and 14 in the book discuss functions from the finite set 1, 2, 3 to itself, and they highlight a really important point. For functions between finite sets of the same size, if a function is 1, 1, it must also be onto, and vice versa. They're equivalent.
So for finite sets, one property guarantees the other.
Exactly. This is because if every element in the output set is hit onto, and you have the same number of elements in both sets, then there can't be any two elements in the input set mapping to the same output, 1, 1. Otherwise, you'd run out of elements to cover the entire output set. And conversely, if each element in the input set maps to a unique element in the output set, 1, 1, then you must have covered the entire output set onto because you have the same number of elements in both sets.
That makes sense intuitively.
It does. And the book emphasizes that this equivalence doesn't necessarily hold true for infinite sets, as we saw in examples 8 and 10.
Right, those examples use the natural numbers, which are infinite.
Precisely. So the takeaway here is that the relationship between 1, 1, and onto is different for finite and infinite sets.
Okay, so we've covered a lot of ground today. We started with the basic definition of a relation, explored different types of relations, including the very important equivalence relations and how they partition sets. Then we moved on to functions, which are special types of relations, and discussed their different classifications: 1, 1, onto, and bijective. These are all fundamental concepts in mathematics.
They are indeed, and understanding them gives us a powerful way to describe and analyze connections and mappings, not just in math, but in many other areas as well.
So, to all our listeners out there, I want to leave you with a thought. Think about a library catalog. You have books, authors, subjects, keywords.
A great example.
Can you spot any reflexive, symmetric, or transitive relations in how the catalog is organized?
It's a great exercise.
And when you search for a book, isn't that essentially a function? You input your search terms, and the catalog outputs a set of books.
It is.
Do the properties of 1, 1 aren't on to apply there? It's amazing how these mathematical ideas show up in everyday things.
They really do. And that's the beauty of mathematics. It provides a framework for understanding the patterns and structures that underpin our world.
So we encourage you to keep exploring these concepts. You might be surprised by what you discover.
Absolutely. There's a whole world of fascinating connections out there just waiting to be uncovered.
And on that note, we'll wrap up our deep dive for today. Thanks for joining us.
It's been a pleasure.